From X, we have one outgoing edge to T with a -2. Everything else is a 0. This matrix is not going to be a symmetric matrix. This is going to be an asymmetric one because it's a directed graph and it does not have symmetries in it. Now we have Y. Y has two outgoing edges, X and Z. Um, so X contains what now? -3, and Z contains 9. Rest S and T should be 0 for Y, I think. Awesome. Can you guys, so if you understood this, how we filled it out, can you guys please in the chat, oh, I should be recording. Hey, thanks, Atish, for recording. Uh, where is it getting recorded to? Okay. My show transcript. Testing, testing, 1, 2, 3. Oh, 1. Okay. We go to the chat. Okay. So can you guys please type in the last row for Z, STXYZ, the last row for this adjacency matrix in the chat window? Z goes. Oh, there is 1 to S. Yes. Right, exactly. Very good, Zach, Ryan, Marcos, and Saurav. Uh, so we have 1 to S with a 2, then 0, nothing to T, nothing on, so going to X with a 7, nothing to Y, and that one is 0. Awesome, very good. Now let us write the same thing as an adjacency list. The adjacency list representation is again all vertices listed out. I am going to follow the same ordering, X, Y, Z. And each of those entries contain the list of edges to their outgoing child nodes. So for example, we will have for S, T comma 6, and we'll have Y comma 7. For T, we will have X comma 5, Y comma 8. And this is the dictionary that we have been creating in that particular code, Z comma -4. X goes to T comma -2. Nothing else. Y goes to X comma -3 and Z comma 9. And Z goes to S comma 2 and goes to X comma 7. Everybody, I hope, agrees with this set of numbers here. I think it should be correct. Now let us first do BFS. BFS basically maintains three things, or let us actually, if we look into it, it is basically the discovery time of different vertices. So we will have our vertex list, vertex discovery time. We will also maintain vertex parent, v dot pi, where it comes from. And we will also maintain a visited node or visited array list. We will list out the vertices S, T, Y, and so on. Hold on, before I do that, let me color code the thing. So S, T, X, Y, Z. So quick question. You guys remember that, so should I be considering weights or not when I'm doing breadth first search? No. How do I deal with negative weights then? Positive weights, I can consider them as single unit cost weights and just do it like that. Ideally, what should I be doing with negative weights, in your opinion? Don't traverse is a good answer, Nirajan, but I would suggest in real life, a negative cost is usually thought of as something that causes a penalty if you traverse that direction. So a negative cost should actually be reversed in my point. Depends upon the problem. In our case here, we will just assume everything as it is and just assume unit cost. But I've seen problems where negative edges are considered reversed. Okay, so don't get surprised if that happens. Hope that made sense. Okay, so firstly, I'm going to set everything visited to false. I'm going to basically quickly go to the breadth first search code just to remind you what that code was. Coloring gray, white, and whatnot. Discovery time is there. There is no finishing time. Depth first search had finishing time. Discovery time is only there for breadth first search because we are not calling this recursively using a stack. We are calling this using a queue. Okay. So there is no returning back. So first thing, what does it do? It sets the source node. Let's consider the source node to be S as well. And it sets that discovery to 0. Every other discovery and parent is set to infinity and null. So I am going to set the parent of this thing to nil, and every other cost here is set to infinity. Discovery time is set to infinity, and every parent is set to nil. Now what does it do? It dequeues that first node from the queue and then inserts all children into that queue and sets their discovery time to discovery plus 1 and sets their parent to the current node. Okay. So what does that look like? Let's go back to the Bellman-Ford graph. We'll be using this graph, but we'll be doing basically breadth first search. Hold on, let me bring up your chat. Cool. All right. So I'll first go over S. So I go to S and I look at all of its outgoing nodes. I have one for T, one for Y. Cool. I'll set T to 0 plus 1, right? Because S is 0. Remember what it does? It basically sets V dot D or V dot D equals to U dot D plus 1, and it sets V dot pi equals to U, right? So that is the point of breadth first search. So I'm going to set T to 1 because U is S. I'm going to set Y to 1 because those are the two nodes coming out of S. And I'm going to set both of these parents to S. That way I know T and Y come from S. Now, whichever one we pick, either way, S has been used up. S has been dequeued from the thing. I am just going to color this red to indicate that it has been removed from the queue. By the end, all of these will be removed. So everything will be red. So that was first removed. Then we pick one of the two. Let's pick Y. Everything has the same cost. So Y has outgoing edges. So we go here. We have two outgoing edges, X and Z. X gets to be 2 because currently Y is U and its parent is set to Y. Z gets to be 2 as well because and its parent, yeah, it would have gone both ways. And its parent is set to Y as well. and these all should be visited by the time. I forgot to change those, but essentially this got true first, then these two got true, and then this and this got true. So these are the discovery times and parent nodes of this particular breadth first search tree in this graph. As you can see, we just did 1 and 2 steps, and we were able to cover or discover the full graph because S2T, T2X, and Y we got, Z we got. So can you guys tell me? Okay, I'm going to give you guys 2 minutes proper. Write the adjacency list of this BFS tree. Could you please type out the adjacency list of this BFS tree? Write it up in a notepad and then paste it here. The question is, I will write one as well. Adjacency list. I will write the wrong version. I want you to tell me what the right version is. So S, T, X, Y, Z. I'm just doing the adjacency list of the tree, not the entire graph. So from S, I go to Y with a cost of 1. From S, I also go to T with a cost of 1. From T, I go to, from Y, I go to Z with a cost of 1. From T, I go to X with a cost of 1. X contains nothing. Z contains no outgoing thing. Is this correct or incorrect? If it is incorrect, let me just type this out in the chat. You guys can edit this thing and return it back to me. So I say this is the adjacency list of the tree. Fix it for me. I want everybody to answer why this is incorrect. X and Z, are they coming from two different vertices? I'll give you till 325. While you do that, let me set up Dijkstra. So Dijkstra will also maintain a value array. It will be from this adjacency list. Let me copy this. Marcos, are we going to anywhere? Your T row is correct. Sorry, your Y row is correct. Is your T row correct? S to Y and T correct. Y to Z and X correct. Are we going to X via T? Exactly. Very good answer. So remember, not all edges are evaluated when you are actually processing the thing. Very good answer. Awesome. Cool. Let's do Dijkstra. I want everybody to sort of type out the answer if you can once you have it for the adjacency list. It should look something like what Zach and Marcos submitted. X, Y, Z. Let's go to Dijkstra. What does Dijkstra do? Dijkstra was just going to insert it, all of the Q elements. It is still going to maintain a discovered and that thing, but mainly it is maintaining a distance to all other vertices. It is basically setting the initial source node to 0 and then extracting out that, going for each child node, relaxing each child node in that order, and decreasing the key if needed. So let us do that. One thing I'm going to change is, since Dijkstra does not like negative weights, I'm going to change these weights to positive weights. We have seen examples where Dijkstra does not like negative weights. We can work on those later if we want to, but for now, I'm just going to set everything to positive. It's a modification on our graph. I think they also have the same similar graph with different numbers, but Ryan, it will not be going via T. So in your case, it might, but S goes to T and Y. If you wanted to explore T first, then yes, T would have gone to X and Z, but not to Y. Y was already explored by S. So it would either be T, X, comma, Z, comma 1, either this, or X, comma 1 slash Z, comma 1, or this. In our case, it is going to be this and not this, because we did not explore via T, we explored via Y. Hope that made sense. Okay, so first things first, everything is set to infinity. So 0, infinity, 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 infinity. Cool. Now what does it do? It extracts it from the queue, the smallest number, and essentially evaluates that. What I'm going to do is I'm going to select the smallest number, indicating that it has been removed from the queue. So I'm removing Ryan, then this would be via T, right? You are saying that your breadth first search tree is explored via not Y, as in my example, but in your separate example, then it is being explored by T. Both are fine because both are 1 unit away. Depends on which one was inserted into the queue first. Do you agree? Awesome. So I extracted out Dijkstra's first node from the queue. We'll be picking the smallest number, assuming there is a heap tree underneath that maintains the smallest number so far. And then what does Dijkstra do? It goes over all children, inserting them to the particular node. Their distance is the distance of the, basically again, v dot d equals to u dot d plus not 1 anymore, weight of u comma v, right? We said that another way to write this was distance of s comma v, s being the source node, equals to distance of s comma u plus edge weight of u comma v. That was our Dijkstra's thing if we were to find the minimum of the two. So in essence, we are saying, let me just say, the distance of s comma v is the minimum of s comma v versus s comma u plus weight of u comma v. Okay. So we are going to go over first insert all children. So I'm going to copy this column. I think I should be moving this downwards. Yeah. So we are going to copy this column. This is just the previous set of values, and we are going to insert all of the child nodes of S. S has T and Y with 6 and 7. So the new cost will also be T equals to 6, that is 0 plus 6. And so what is offered? Currently the value is infinity. We are offering 0 plus 6, so that is 6, and the value then becomes the smallest of the two. Infinity versus 6 becomes 6. And same applies to y. Currently it is infinity. We are offering 0 plus 5, so that's a 5. So this becomes the minimum of the two, so that's a 5. Of this now, 0 was already exited out. The next thing to be exit out is basically this thing. That is the smallest value so far. I'm going to copy this thing into a new column. And now we are going to extract from y. From y, we see there are two children, x and z. X gets the currently is infinity. You are offering what? Guys, what are you offering to x? Currently it is infinity. S to x is infinity. You are offering s to y plus ys cost. Yx cost. 8. 540. S to Y, Zach, S to Y currently is 5, right? No, what did I do? Why did I offer 5 here? I made a mistake, right? S would get 6 and Y would get 7. So this was offered 7. This becomes 7. This was offered 7. This becomes 7. This is no longer the smallest one. Sorry. No, Phil. Thanks, Zach. This one was the smallest one, and this one will be evaluated. We are asking S to T, and T now has X, Y, and Z. I see the issue. Hold on. I'm going to go back to the Bellman-Ford graph. We are going to maintain the same graph. We are going to maintain our graph here. We are not looking at the graph from the book. We are solving our own adjacency list graph. This one, we are not going to be looking at the book because we are not following that one. Sorry about that. So we are following this graph here. This graph is just basically the Bellman-Ford graph. Negative weights have been made into positive weights for now. So, for example, T2Z was -4. T2Z is here just 4. Zach, does that make sense? Awesome. Thank you, Zach. Thank you for bringing that up. Okay. So I am going to explore T now. I'm going to look at T's child nodes, and T is going to now offer for X, it is going to offer 6 plus 5. So T is offering for X, that is 11. X is currently infinity, so 11 gets accepted and the new value becomes 11. T2Y is 8. Y is currently 7. You are offering S to T, that is 6 plus 8. So you are offering 6 plus 6, 12, comma 2, 14. So you are offering 14 and Y remains 14. Do you guys agree with this statement here? Please type in yes or no. So this cost here was S to T, T to Y, and it just offered 14 and it remains 7 because 7 is the minimum most value. Why are we able to modify this thing? Remember, Y has not yet been green. Y is not yet extracted from the thing, so I can modify this thing. Okay, remember Dijkstra says, the moment I remove the smallest one, I will never again find a smaller value. But if there are other variables there, I can decrease those values. That's fine. So this is a new offer that we just got. And then it also goes to Z with a cost of 4. So currently it is infinity. It is offering 10 and it becomes 10. I'm now going to copy over the full thing, but I think this is the next smallest one to be extracted. So I'm going to create a new column. And now I'm going to ask from Y, what are the outgoing edges? So I have one to X and one to Z. X is currently 11. I am offering 10, right? 7 plus 3, I am offering 10. So we update X and we pick the new minimum. Now we are offering to Z, which is currently 10, the cost of 7 plus 9, which is 16. So I am offering 16 to this thing. It remains 10 because I have a smaller value. Now, out of this two, we both have the same thing currently, but let us actually just pick Z because it was here first. And we are going to copy this full thing. And we are asking to explore Z. Exploring Z, we get Z to S is 2, right? So Z to S is 2. So what are you offering? Z itself from S is 10. So you are offering what? S 2 dot dot Z dot dot S to Z. From Z, you are now offering to S, right? This is what you're offering right now. So S to Z is 10 and plus 2, you are offering 12. And S remains 0. Obviously, the next thing you're offering is to X. For X, you are offering 10 plus 7, so 17. And it remains as it is because 10 is the smallest value. And then basically we are going to extract that out. I'm going to create one more copy, but essentially we end up with these values: 0, 6, 10, 7, and 10. Assuming these are all positive weights, S to S is 0, S to T is 6, S to X is 6 plus 5 is 11. How did it go to X? 7 plus 3. So SYX is the path taken by Dijkstra for 10. And then we have for Y is S to Y, that's 7. S2Z is 10. How did I get there? Well, STX, or sorry, STZ, 6 plus positive 4 is the total cost for Z. Does Dijkstra make sense? This worked out example. I forgot to do the parent thing. I should have done the parent thing in addition to this thing. But yeah, the parent list would look something like this. So V dot pi will basically look like this. So let's say this is S, T, X, Y, and Z. SS parent is nil. T's parent is S. Y's parent is S. X's parent was via Y, I think. So Y. And Z's parent was via T, I think. So T. So that would be the parent graph of this thing, which you can use to sort of print out or list out the actual graph as well. This tree is different from this tree though, isn't it? Anywho. Any questions about Dijkstra? Cool. I'm going to list out the variables again, ST, X, Y, and Z. Again, remember it is maintaining a value array. The output of Bellman-Ford is a value array, right? Every Dijkstra is also a value array. These are all single source shortest path algorithms, which mean that the input is a graph and a source node, and the output is an array of distances from S to vertex V belonging to capital V. Okay. Cool. I'm going to now copy over the adjacency, original adjacency list with negative values. I say what? Let's do it with positive values. Bellman-Ford will be the same no matter what. But just to keep the sense of how Dijkstra does it and how Bellman-Ford does it, I'm going to be using the same adjacency list. Okay, so this one, I'm going to copy it over and paste it above Bellman-Ford. Okay. So what does Bellman-Ford do? Bellman-Ford was just these three lines. The rest of the lines were just doing it once more to check for negative cycles. But essentially, for V minus 1 times, why V minus 1? Because we said that if there are no negative cycles, but there are negative weights, it can, let me move my hand around a bit. Let me show my face. Hold on. So you guys remember that for Bellman-Ford, essentially what did we say? We said that if we have negative weights, the negative weights can sort of come back from very far after, right? So we will need to update at least V minus 1 times, because that is the length of the maximum length of a shortest path string, right? So for every new step or every new vertex that we find, there could be an edge coming back with a huge negative value, which we do not know. So we might need to update the original cost of those other vertices. That is not the case for Dijkstra, because everything is positive, everything will go up. But Bellman-Ford, something can go down. So with negative values, Bellman-Ford will also work, but without negative cycles. I'm going to turn off my camera. Hope that made sense. Otherwise, ask me in class. Okay. So coming back, what does Bellman-Ford say? Well, Bellman-Ford, it doesn't say that it is setting it to 0 initially, right? It's just relaxing. Cool. Initially, Bellman-Ford will set these values to all zeros. Oh, sorry, set the first node value to 0. So S is 0. Everything else is infinity. Remember though, Bellman-Ford does not have any priority queue or any stack. It just says v minus 1 steps, update every edge every time. It contains a source node. It initializes the single source to 0, I guess. But apart from that, it does not care about adjacency list. It does not care about other child nodes. It does not care about anything. Okay. So what we are going to do is we can literally just randomly pick all of these edges in random order, and we will still be ending up with the correct answer. Now, just to make you guys understand that I can move around this thing into a random order, but what I'm going to do is I'm just going to follow this order. You guys do understand that you can very well have written this down in a different order, X, Y, Z, T, Z, S, right? That would have been fine as well. I'm just doing this like this. So the edges are basically S comma T, then we will have S comma Y, then we will have T comma X, then we will have T comma Y. And these will also contain costs. I'm just being lazy. T comma Z. You do not need this. You will just be reading from the adjacency list step by step, each child at a time, and just updating it. Bellman-Ford just does not care in which order you update them. Then we have Y comma X. Then we have Y comma Z. Then we have Z comma S and Z comma X. So Z comma S and Z comma X, right? So let's start. We are going to update every edge, and every time we are going to ask the same question, this question, where the edge that we are considering is going to be this W edge. Okay. So we have this. Let us start. I'm going to copy this over. No priority queue, just copying this over. And now I'm going to do first S2. Let's do it in a other order. Yeah, let's do it in another order. Hold on. I'll start from T and do the SS at the end. I can do it at the end, but let's do it just before the Zs. Do you guys notice that I have this in a different order? Could you please type in yes or no? It's just another random order of edges. Ryan says yes. Shankar Zach says yes. How about everybody else? Saurav, Sandhya, two mains, Atish, Kalyan, Shankar, Nirajan, Bhuvan, Kashif, Uha, Sravya. Awesome. Good. So I'm just going to pick this up. So let's say T2x. T2x cost is 5. Currently, this is infinity. What are you offering? You are offering S to T, T2x, right? So that is 0 plus 5. So you are offering 5. This becomes 5. Next, we are doing T2y. T2y is 8. Currently, it is infinity. You are offering 0 plus 8. So you are offering 0 plus 8. So this becomes 8. S2 T. No, you are not offering this thing. Okay. So let's do T2x first. So T2x, the first edge. Can you guys tell me what am I trying to update? Which value am I trying to update with T comma x? Am I updating S or T or X? Which row should I be updating? X. X, not T. Remember, we are trying to find we are trying to find S to V. V is the last vertex here. T is the via vertex that you are looking at. Humans, does it make sense? Awesome. So we are trying to update X. Currently, what are we looking? We are saying, let me type this explicitly, it will make more sense. We are saying d of s comma x is the minimum of d of s comma x or d of s comma t plus weight of t comma x, right? So that is what we are saying. I'm going to delete this thing. So do you guys agree s to t currently is infinity, right? It has not yet been updated. So I am going to just say this is offering currently is infinity and it is offering infinity plus 5. So it is still offering infinity and it remains infinity. Next is t to y. S to t is still infinity. I would have updated this y to something else, but it is still going to remain infinity. So no update. T to z. I should have updated this to something, but S to T is infinity. T to Z is 4, but that just remains infinity. Infinity plus 4, so that's infinity. Next is X to T. X to T, so I'll be updating T. S to X, I'm going to delete this now. S to X is currently infinity. Current values, I will always be looking at the previous column. New values I'll be updating in the current column. So whenever I'm looking up values, I'll be looking in the previous column. Okay, so S to X currently is infinity. X to T is 2. So we are again offering to T infinity, so I don't care. Now we have Y to X. So I'll be updating X. S to Y is currently infinity plus Y to X is 3, but don't care, remains infinity. Y to Z. S to Y is currently infinity. Y to Z is currently 9. So we don't update anything there. Infinity plus 9, so that's infinity. Now comes S to T. Okay. S to T is basically saying D of S comma S plus weight of S comma T. And we are trying to update D of S comma T. Okay. So in that scenario, D of S comma S is 0. Weight of S to T is 6. So we are offering something. So T is currently infinity. We are offering 0 plus 6. S to S plus T, S to T, which basically becomes 6. So this becomes 6. Now we are doing S to Y. S to S is currently 0. S to Y is currently 7. So we are offering 7. This becomes 7. Now we are looking at Z to S. S to Z is currently infinity. Infinity plus Z to S is 2. Infinity plus 2 remains infinity. Z to X, by the same logic, S to Z is currently infinity. And Z to X is 7. It remains infinity. I hope this column makes sense. Also note, even if we updated every edge, since only S had a starting value of 0, Only the child nodes of S get a legit value. Everything else gets a wrong value. Now we are going to go here and we are going to do this process again, v minus 1 times. So ideally, I'll have to do this in total 4 times, right? Because there are 5 vertices. That's why time complexity measurements are good. You know how many times you have to copy, right? And do these things by hand. Okay. Now, again, I'm going to start from the very beginning. Remember, what did Bellman-Ford say? Who cares about what the starting node is? Who cares about what the lowest cost is? I don't care about anything. For every edge, update everything. So again, T2X is going to start. So T2X, I'm going to be trying to updating. I'm going to try and update X. So with this value, I'll be updating S to T plus TX. S to T currently is now 6 plus Tx is currently 5. So I am offering 11. This was infinity, it becomes 11. Do you guys agree with this update right now? Who says yes? Zach says yes. Everybody, I think, should say yes to this one. Awesome. Now, T2y. T2y, y currently comes from S, but let's see what it is offering. It is currently offering S to T plus Ty. S to T is currently 6 plus Ty is currently 8. 6 plus 8, so that is 14. So it is offering 14, but it remains 7. Remain very similar to what Dijkstra did. Anyway, but Dijkstra did not have, Dijkstra also had 11 here. Cool. Now, the next thing is TZ. TZ, T is currently 6. S to T is currently 6. TZ is currently 4. Did I make a mistake? 6 plus 8 is 14. Yeah. T is currently 6. T2Z is currently 4. So it is offering 10 and it becomes 10. We will be updating everything. We are not yet done. Then we have X to T. T is this one. Currently T is X. Sorry, T is 6. Currently X, we are going to current values. We are always going to look at the previous column. So X is currently infinity. We are offering S to X infinity and X to T is 2. So we are offering infinity. So it remains 6. Then we have YX. So that is S to Y, which is currently 7. And then YX, that is 3. Ooh. So YX then becomes 10. We are offering 10. And this is basically going to update itself to a minimum value of 10 for this YX, right? Because S to Y is currently 7, YX is 3, so it is offering 10. Next is YZ. S to Y is currently 7, YZ is currently 9, so it is offering 18, right? 9 plus 7, it is offering 16. It remains 10. Next is ST. S to T is currently 6. It is offering 0 plus 6. It remains as it is. So it just is 6. Next is SY. SY is currently 14. We are offering S to S is 0 plus S to Y is 7. So it is offering 7. It remains 7 as well. Then we have ZS. That is S to Z, Z to S. S to Z is currently infinity. Z to S, ZS is currently 2 or ZS is 2. So you are again offering infinity here because S to Z has not got the original value in the previous column. That is, we are always going to look at the previous column just to make sure we can use the same column in code, but this is just to, understand it better. So that's that. And then ZS is done. Now ZX. X is currently 10. S to Z is currently infinity. ZX is 7. We are offering infinity. So it remains 10. So that is the current set of values that Bellman-Ford has. Ideally, this should be the last one. And we already in the best number 6, 10, 7, 10. 6, 10, 7, 10 is already there. Do you guys agree that if Bellman-Ford's answer, I know this is the third one, if it does not even change now, it will never again change, right? Okay. Now let's see. Going at it again, we start with we start with TX. Okay. So for TX, I will be updating X. I'll be offering something. Can you guys tell me what am I going to offer to this particular first edge? TX, what is it offering? For TX, what will it offer? S to T plus TX. Eleven. Exactly. Very good. So it is going to offer 11. S to T is, in the previous iteration, we saw it's 6 plus TX is 5. So it is offering 11. It remains 10. Now comes TY. S to T in the previous iteration is 6. And we are offering plus TY 8. 6 plus 8, that's 14. We remain 7. Then we have TZ. S to T is 6. What are we offering? 6 plus TZ, 6 plus 4, so that's a 10. It remains 10. Now we have XT. So we are trying to update T. S to X is currently 10 and XT is 2. Do you guys agree that we are going to offer 12 here? Because we are updating XT, this one, and it is X S to X plus XT. So this is basically S to X and XT. If everybody of you agrees, why wasn't 12 offered before? Kindly, if you want to speak out, uh, instead of typing, if you want to discuss, why wasn't 12 offered before? I know it is not the best answer, but why was this number not offered before? 14 was offered before, 16 was offered before for these cases. Why is 12 the first time we are saying this? Yes, there was no path from S to X until the previous iteration. It explored and it came to X after 2 iterations. Remember, in Bellman-Ford, the topmost iteration that you see, V minus 1 iterations, that is also the controller of path length. It also tells you how long, like BFS path lengths, not cost-wise path length. Individual edges are individual things. So it is going to grow by one edge every time. So Bellman-Ford's V minus 1 loop basically increases the allowance of the path length by 1 every time. So you are saying what is the shortest path if I only allow one edge to all other vertices? What is the shortest path if I only allow two edges for any path? What is the shortest path if I allow three edges for every path? Four edges for every path, five edges for every path? Cannot happen, because I know at max there will be v minus 1 edges in any path. Does that make sense? The allowance of path as it increases. So first iteration, you are saying only allow one edge to go to all other vertices. I cannot go to X and Z with just one edge, but I can go to T and Y. Now you are saying allow two edges in the second column. You are saying allow two edges. Now I can go to X using two edges because I had the opportunity to go 7 plus 3, 10. So two edges are allowed. Now it is 12 because S to Y to X to T is now being offered. 7, 3, 2. Now we are allowing three edges, and that is why this 12 is getting offered. And that is why V minus 1 edges, because you cannot have more than that. Does that make sense a bit? Like the edge allowance thing. Over iterations. First iteration, Bellman-Ford inherently allows one edge to go to every other place. Second iteration, Bellman-Ford is allowing two edges to go every other place, three edges, four edges, and so on. If you guys don't feel like typing, feel free to speak. That also works. I'm going to then assume it makes sense if none of us say anything. Okay. So that is why 12 comes in. Very good. Now I'm going, did I complete all of those? So I did not, right? I just did X to T. Now let's do Y to X. So I'm going to be updating X. Currently it is 10. S to Y is 7. YX is 3. So I'm going to be offering 10 and it remains 10. Now we have YZ. So currently it is 10. S to Y is 7. YZ is 9. So 7 plus 9. So that's a 16. So we are offering 16. It remains 10. Then we are looking at ST. S to T is currently 6. We are offering S to S plus ST. So that is just 6. So it remains 6. Now we are doing SY. S to Y is currently 7. S to S is 0. SY is also 7. So we are offering 7. Remains 7. Now we have ZS. So we are trying to update S. S to Z is currently 10. ZS is currently 2. So we are offering 12. It remains 0. Obviously. Now we are looking at ZX. X is currently 10. S to Z is 10. ZX is 7. So it is offering 17. It remains 10. So S X 6, 4, 7. That is the three edge path being offered. S to T, T to Z, Z to X. That is 6 plus positive 4 plus 7. That is the 17 that was offered. And that was also the first time we are offering it because it is a three edge path. Do you see that none, even if we are offering new things in this iteration, agreed? We offered a couple of new things in this iteration, but none of them got updated. The previous values are the same values. Guaranteed then we will never again find a better path. Even if you have offered something new this iteration, doesn't matter because the final costs are the same. So you cannot get a better path. I'm going to do it once more, but ideally you see that we have done it for V minus 1 steps. Oh no, we have not. We have done it for 3 steps, right? V minus 1 would be 4 steps. The first one is just the initialization step. Ignore that. We have done it for 3 steps. So ideally, in the fourth step, should be when we stop, but we can stop right now because none of these have changed. Since none of these have changed, it will never again change. But I'm still going to do it once more just to see what would be offered next time around when we allow paths of 4 edges, not just 3 edges, but 4 edges. But I know for a fact nothing will change because nothing changed right now. Okay, so these are the costs so far. We are going to go back to those. Okay, so again, hmm, cool. So Tx, so that is S to T and Tx. So I'm going to be updating X, comma. What am I offering? Currently it is 10. What am I going to offer? Well, S to T. S to T is currently 6. Tx is 5. So I'll be offering 11. It is currently 10, so it remains 10. Then we have Ty. S to T is 6 and we are offering S to T is 6 plus Ty is 8. So we are offering 6 plus 8, so that's a 14. It remains 7. Then we have Tz. Currently it's 10. We are offering S to T, that's 6 plus Tz is 4. So we are offering 10 and it remains 10. Oh, I should have maintained the dot pi as well. I forgot to do that. Anyway, then we are doing Tz is done. Now is xt. So T is currently 6. We are offering Sx plus xt. Sx is S2x is currently 10 plus xt is currently 2. So we are offering 12. It remains 6. Then we have yx. Yx is going to update x. Currently x is 10. S2y is currently 7. 7 plus yx is 3. So that's 10, remains 10. Then we have yz. So we are trying to update this, which is currently 10. S2y is currently 7. YZ is 9. Ooh, that's 19. It is offering 19. It remains 10. Can you guys tell me, this was a new offer, right? 19 never was not offered again. Can you guys tell me which path was offered? It should be a 4-edge path. Comes from TZ, right? 6 plus, no, YZ. So S2Y is 7. I did wrong, didn't I? It's not 19.
It should be 16, right? Because we didn't change
Right,
the value of y in the previous
right.
iteration.
No, it should be 16 because it
Sorry.
is
Yeah.
right. It's if which one was I doing? TZ, right? So S to T is currently 6 and TZ is currently 4. So that's 10. Oh, that one was the previous one. I think I was doing YZ. YZ is essentially S to Y is 7 and YZ is 9. It should be 60. My bad. Yes, 60. Very good. It remains 6. It remains 10. Then we have ST. ST is basically S2S plus S2T. S2S is 0 and ST is 6. It is currently 6. We are offering 6 again, remains 6. SY, it is currently, where was it? Y? It is currently 7. S2S is 0. SY is 7. We are offering 7. Happy days, it remains 7. Now we have ZS. So S2Z is currently 10. ZS is currently 2. So it is again offering 12. Keep on offering. That remains 0. Now we have ZX. Um, S2Z is currently 10 and ZX is currently 7. So we are offering 17. It remains 10. Agreed? Any questions about this thing? We are done. Cool. Now we are going to do shortest path DAG. We are not going to be able to do this on this graph because it's not a DAG. This only applies for DAGs. So what we are going to do instead is I am going to use the example here and we are going to do the DAG on this thing. I'm going to create an adjacency list representation of this graph and then do a topological sort, and then we are going to do this. What I want us to compare this with though is Dijkstra. In Dijkstra, what was the first one to be evaluated? S. Then what? T. Then what? Y. Then what? I believe Z. Then what? I believe X. Right? Those were the order in which these were processed. I want us to note when we will do shortest path DAG, how even if it's a graph, remember for shortest path DAG, the time complexity is just of that of V plus E topological sort. That's it. No log V, no V cube, nothing. Like Dijkstra's time complexity was what? We go of V plus E log V, right? What was Bellman-Ford's time complexity? Well, that was big O of VE, V minus 1 times update every edge, right? That was basically V cubed. Shortest path DAG, on the other hand, will be big O of V plus E. It just needs a topological sort. That's it. So let us see that in order. So I'm going to list out the vertices R, S, T, X, Y, Z. Wow. Okay. Now, initially, what do? We set the distance of the source node to 0. Everything else is going to be set to infinity. But before we do that, we will do a topological sort of the thing. So first, let us actually have this graph. R goes to S with a cost of 5. R goes to T with a cost of 3. S goes to T with a cost of 2. This is in page number 618. And S goes to X with a cost of 6. Negative costs are fine here because there are no cycles. Everything is fine. Uh, T, and also remember, shortest path DAGs are important because this is what you use to solve knapsack and all other dynamic programming problems, which is E squared or number of edges squared time complexity, which is that for knapsack as well. Anywho, um, T is going to be going to X with 7. Why is knapsack shortest path DAG? Because for knapsack, we drew a tree, the recursive call tree. There are no cycles in that tree, so it's a DAG. The cost could be negative or positive, but it's a tree. Trees are always DAG, and the shortest path is the best sum problem of that particular tree. X is basically 7. T goes to Y with a cost of 4. T goes to Z with a cost of 2. X goes to Y with a cost of -1. X goes to Z with a cost of 1. Y goes to Z with a cost of -2. Z goes nowhere. Cool. If that is the case, I want you guys to please give me the pre-visit, post-visit numbers of this graph. R, S, T, X, Y, Z, or work them out with me. S starts at, hey, did we start our pre-visit, post-visit at 1 or 0 in our class examples? Sure, not from 1. I always did, let me share my camera. Hold on. So when I did the pre-visit, post-visit number, so 1 slash that thing, it was never, I think the book has it as 0 slash something, but 1 slash something is also fine. Let's stick to 1 slash something. Fumens, you okay with that? If we do 1 slash something? Cool. Camera off, share screen on. So we start from S. S is 1. Then we go to either T or X. Well, let's go to T. T is 2. From T, we can go, let's also always just use the adjacency list to do the thing. From S, I pick the first one, I go to T. From T, I'll take the first one, unless visited, I'll also have the visited node. Hold on. So S is visited. T is visited. Cool. From T, we will go to X, the first one. Remember, it's a depth first search, so I'll just pick the first available one. So X becomes 3, and that's also visited. Visited as in gray node, not white node. Definitely no black nodes yet. Then from X, we are going to Y. Cool, that works. So that gets 4. Y is visited as well. From Y, we are going to Z. This looks like this because it is already sorted like that. Y becomes 5. Y is also visited. From Y, it is going to Z. Z becomes 5, sorry. And then Z finishes. So Z becomes 6, goes back to Y. Y just had Z to do. Z is done. So Y becomes 7. Now it goes back to X. X dealt with Y. Now it is trying to deal with Z. Z is already visited, so it does not care, closes this thing to 8. Next, it starts off with T. Note that R is not yet touched. You know what? I'll start with R. Doesn't matter which way we start from. We do not have to start from the source node to find the topological sort. So I'm going to start with R, knowing that I think the previous one was better. If I started with R, it would have done the full thing in one go. Let's stick to this one. This is much better because R is still empty. Now, T basically is going to, so we are reverting back to the previous example. We are here. So T finishes off. T had X done. Now it is looking at Y. Y is dealt with. It now looking at Z. For all children, it is going to call the explore function if not visited, right? So X it called. Then it is trying to call Y, cannot do it. It is visited. Z it cannot because it is visited. So T finishes off with a 9. Then we have S. S tried with T, explored all of those things. Now it is looking at X. X is already visited via some other child. So it finishes off S. That is done. Now it goes to the outer loop, right? DFS had two loops, right? It now goes to the outer loop to finish off all other disjoint vertices. In this case, R is technically disjoint because we started at S and no path goes to R. But now we are going to start R at 11. Everything else for R, S and T are both visited. So R finishes at 12. Do you guys agree with this particular pre-post visit numbers and the topological order of R, S, T, X, Y, Z? Please type in yes or no if it makes sense. Awesome. Now, what does it say? Well, where is the algorithm? For each vertex taken in topologically sorted order, starting from the largest post visit number, that is for R, and going towards the smallest post visit number, which is the sink. So starting from the source, going to the sink. For each vertex that is a child node of that particular source node, relax that vertex. Okay. So we are going to create our value matrix like before. So this will be shortest path DAG. R, S, T, X, Y, Z. Do you see the prediction of this thing is so good? It first detected shortest path for S, but this time it remembered that S is just on its own. Okay, so initially it is going to set everything to that same thing. So S is 0, everything else is infinity. So S is 0, everything else is infinity. And now starting from the source node, that is the one with the, starting from the R node, we are going to look at all both children. So how are we going to update? We are first looking at S. So R2R plus R2S, sorry, S2R, R2S. S2R currently is infinity. These are all values, okay? S2R currently is infinity, S2S is 0. And you are offering what? You are also offering infinity plus 5. Oh no, infinity plus S2R. Does not even exist. Sorry, RS. Relaxing UVW. And we're from there, we are updating that node. Okay. So what are we asking? We are asking for the value of R. So S2R and R2R. R2R is 0, S2R is infinity, so it remains infinity. S2S, then R2T. R2T, S2R is infinity, RT is 3, so it remains S2T remains infinity. By the way, we have evaluated this node. I'm just going to copy over the other values for now. We have evaluated this thing. What is the next thing we are going to evaluate? Well, in topological order, S comes next. So let's evaluate that. For all outgoing children of S, we have T and X. So we just update T and X. That's it. S to S is 0. ST is 2. So it is currently infinity. We are offering 2. This becomes 2. Let me copy. So S to T, so we are just looking at the outgoing edges of S, not over all edges, just S to T. So S to T currently is infinity, and it is going to be offered S to S plus ST, so which is 2, so it becomes a 2. Next is SX. S to S is 0 plus SX is 6. Currently it is infinity being offered 6. So it is now going to become 6. As you can see, T and X have also become 2 and 6 as per our rules here. We don't look at anything else because we don't care about the numbers at all. We are following this order, right? We just did R, then we did S, next is T. Cool. So T will be evaluated next, not because of the smallest value, but in general, even if it was 20,000, we would be doing T first. So we copy this, we paste it here. And now we are saying, do you see also how these are getting evaluated step by step? So for T, we have X, Y, and Z. So T2X, X is currently 6. We are offering STTX. ST is 2, TX is 7. So we are offering 9. It remains 6. Now we are offering TY is 4. S to T is 2. TY is 4. So we are offering 6. And it becomes 6. Y becomes 6, right? As you can see in the first iteration, Y becomes 6. Ideally, Y should be 5. We will see how it becomes 5 later. But for now, Y becomes 6. Now Z. S to T is 2. 2 and TZ is 2. So it is offering 4. It becomes 4. Which one will be evaluated next, guys? Z or X? Guys, do you agree with Marcos's answer? Awesome. Because in topological order, T is next. Sorry, X is next. Doesn't matter if whichever one is smaller. So we are now going to evaluate out this thing. So from X, and let me copy. From X, I have Y and Z. Y gets to be offered SX and XY. SX is 6. XY XY is -1. So it is offering 5. Ooh. And now it becomes 5. Marcos, it is Z. Z, sorry, not Z, X. X. Sorry, Marcos, it is X. Y has become 5. Sorry about that. Y has become 5. And now we are looking at XZ. So Z is currently 4. SX is 6. 6 plus XZ is 5. So it is offering 5. It remains 4, right? And that's that. And finally, we will be extracting Y, which will just update 1, that is Z minus 2. So S Z minus 2 is basically via Y. So SY is currently, I believe, 5, and we are offering 5 minus 2. So we are offering a 3. So this becomes a 3. And then later down the line, even this will get extracted out, but nothing else gets done. Does this make sense? So let me check. So infinity 0, 2, 6, 5, 3. Cool. Any questions about this workbook or what we did so far? I'm going to upload this on Discord. You guys feel free to download it from there. Where did I save it? Yeah, I uploaded it to desktop, right? SSP. Yeah, that's the workbook. I'll also copy the full thing. What? How did this happen? I hold on. Somehow there is a multiple copies of this thing here. File new sample paste. Yeah, file save as. Ooh, quiz is not pushed back to Thursday, by the way. Everybody found the quiz, right? I know I said it's a 2-day quiz, but it ended up being a 7-day quiz. Try to work on the thing. We'll discuss it on Thursday as well. Um, And also I'll paste the thing. I don't know if that helps. Okay. Can anybody find the sheet? Atish, there is no, you can use the current code as the starter code. There is no starter code per se. You do not have to submit code so much, so in more as if you have to explain to me which of these algorithms work better with online versions or offline versions, which of, if the graph changes, um, what will be the required thing for Dijkstra, what will be the required thing for Bellman Ford, and so on. Yes, two means we will have a class tomorrow in person. Thursday's class I'm planning the next, this Thursday's class I'm planning online, like today's session, same time at around when was our class? 4, right? So at 4 we'll have an online class on Thursday, but Tuesday in person class. Let me type it in. Tuesday in person, Thursday MS Teams, normal class times. Cool. Make sense, everybody? Okay, I've also seen some of you have some issues with the assignment grades. If that is the case, meet me tomorrow after class. I will discuss it with you and I'll fix it. Nothing to worry. If I'm missing any emails from you guys, just let me know. If any of you missed a quiz or anything, I'll be posting a missed quiz, makeup quiz online as well within this week. That way, if you missed either quiz 1 or quiz 2, you can make up that quiz as well. Apart from that, thank you guys so much. That's pretty much it for today. If you have no other questions, that's it. Thank you. Bye. Bye, Shankar. Thanks, Marcus. Yes, Zach, we will get our quiz grades. Our TA sort of left, so I'll be grading them very soon. Don't worry, there was an issue with the TA thing. The TA that I showed, met with, introduced you guys to, he could not be the TA anymore. So just give me 2, 3 more days. I'm going to get you all the grades. I'm planning to get you the grades before the break. Thank you. Bye, guys.